Okay, hello everybody. So, in today's Physics 121 video, the first thing we'll explore is the magnetic force on a current. And then after we've done that and looked at an example, we'll start to talk about something called motional EMF. So, if we pull a conductor through a magnetic field, motional EMF will result in a voltage difference across the two ends of that conductor. And so those are the two things that I hope to examine in this video. So what we know so far is that for a point charge moving in a magnetic field, say B, the force on that point charge is equal to QV cross B. And so this tells us a few things. This is kind of a review of some of the things that we talked about in the previous video, is that the magnetic force is equal to 0 if V is equal to 0. So there's no force, there's no magnetic force on a stationary charge. This magnetic force is equal to 0 if V is parallel to the magnetic field, or anti-parallel for that matter, because then the cross product will vanish, because the cross product has a magnitude that is proportional to the sine of the angle between those vectors. And if that angle is 0 or 180 degrees, the cross product will vanish. And the magnetic force was perpendicular to both V and B. Okay, so commonly we don't have, we don't always just have isolated point charges moving with some velocity. We often have a collection of charges, say conduction electrons, in a wire or something. And so let's try to determine the magnetic force on a current in a magnetic field. Okay, so we'll start with a picture, and we'll say that we've got some wire that has some length L, and we have a current I in that wire. Okay, so if the current is moving in the direction indicated, then what we could imagine is some point charge Q in that wire moving with some drift velocity V in the same direction as the current. Okay, so delta Q divided by delta T is current, so if we multiply by the delta T, then the amount of charge that passes through some cross-section of the wire in time delta T is I times delta T. The time for our charge to flow through a segment of wire of length L is delta T is going to be the length of the wire divided by whatever the speed of our charges are. So that's going to be, say, the drift velocity for the current I. Okay, so that means delta Q is equal to I, and then delta T becomes L over V. Or delta Q times V is equal to I times L. If we look at our force for a point charge, it contains this charge times velocity. And so we've calculated something like that. Charge times speed is I times L. In order to evaluate a cross product for the magnetic force, we need to express this delta Q times speed as a delta Q times velocity. So in order to make delta QV equals IL a vector equation, I'm going to define a length vector L. And so how it's going to be defined is that the magnitude of this vector is just going to be L, the length of our section, our segment of wire. L is equal to L, the length of the wire segment. Okay, and so the direction of L is going to be determined by the current direction. Okay, so I mean that's going to be convenient because if we have currents in like thin wires, then it's kind of clear what direction the current is going to. It only can go one of two ways along a thin wire. And so that means this vector L is going to look like this. So it'll start at one end of our wire and it'll go to the other end, and its direction is along the direction of the current. So if we make that definition, then what we can do is we can say, well, delta Q times velocity now, instead of just the speed, is I times L. And that works because our velocity vector is also in the direction of the current. So the length vector L and the velocity vector V are parallel, and they're both in the direction of the current. Okay, so therefore the force on our current segment is the magnetic force is the charge, which we've called delta Q in this case, and then it's V cross B, but we're just going to make the substitution QV is I times this vector L. And so what we end up with is I L cross B is the magnetic force on our current in a magnetic field. So this is the magnetic force on a current in a magnetic field. Okay, good. So that's the first result. And so let's do an example. So example. The force between parallel wires. Okay, so the scenario is the following. We've got one wire in which we establish a current I1. And then we have a second wire in which we establish a current I2. And I'm going to draw it as if I2 and I1 are parallel, but we're going to imagine what would happen if we, say, reverse the direction of I2. So for now, let's draw them as they're parallel, as if they're parallel. The distance between these wires is D. And so the question is, what is the force on wire 2 due to the current in wire 1? So what is, I'm going to move this down a little bit, actually. I'm going to save some room for a picture. So what is the force on, say, wire 2 due to current I1 in wire 1? All right, so what we have to do is first thing, notice that we haven't turned on any external magnetic field in this problem. So there's no uniform magnetic field, say, created by some other mechanism, a solenoid or whatever. We just have two currents and that's it. Okay, so what we have to remember is we calculated the magnetic field due to a long current carrying wire. One of them ways to do it is with Ampere's law. And so let's just recall the result. Recall that a long straight current creates a magnetic field which was given by B is equal to mu naught I over 2 pi d, where d is the distance from the wire to the observation point. Okay, so that means that, say, wire 1 with current I1 is going to create a magnetic field in the vicinity of wire 2. So therefore, wire 1 creates a magnetic field, let's say B1, in the vicinity of wire 2. So if we have a magnetic field B1 at wire 2, which has a current I2, then we should expect that there should be a force on that current carrying wire. So this magnetic field exerts a force on the current I2. Okay, so B1 is equal to mu naught I1 divided by 2 pi d, and so this is the magnitude of the magnetic field vector B1 at the position of I2, because we said our two wires were separated by a distance d. Okay, so the force of wire 1 on wire 2 is going to have a magnitude of, well, let's just write that expression. So it's going to be I2 times L cross B1. So it's going to be equal to I2 times, say, L2 cross B1. Okay, so let's think about that a little bit. we're going to have some vector L2, which looks something like this. And there's going to be a magnetic field due to I1. And so if we do the right-hand rule, let's put our thumb in the direction of I1 so it points towards the right edge of the screen. And our fingers curl around. And so there's a magnetic field, B1, that goes around the wire I1 in the way that I've drawn here. And so that means below the wire 1, the magnetic field B1 is into the screen. Okay, and then just for completeness, we could draw some of the field lines above the wire I1, and in that case, they're coming out of the screen. So this is B1 due to I1. Okay, so with the vector L2 going to the right, and with the magnetic field B1 going to the direction that is into the screen, then if we did the right-hand rule for cross products, we put our arm in the direction of L2. Again, it's towards the right of the screen. We curl the fingers of our right hand in the direction of the magnetic field into the screen. Our thumb's going to point up. And so what we would say then is that the direction of F1 on 2 is up if I1 and I2 are parallel. What would happen if we switch the direction of I2? Let's make I2, let's imagine now that it is going in the opposite direction of I1. When we do the cross product, now L2 would flip directions, and so our right arm would be pointing to the left of the screen. Our fingers would curl in the direction of B1, which is into the screen still, and the force on I2 would be down towards the bottom of the page. And so if the two currents are anti-parallel, the direction of F1 on 2 is down if I1 and I2 are anti-parallel. So one way to summarize this observation is that parallel currents attract and anti-parallel currents repel. Okay, and that's all deduced from the right-hand rule. So let's see if we can do the magnitude of this force. So the magnitude of the force is just going to be F1 on 2. I'll drop the vector sign. And so it's going to be I2. And the magnitude of L2 is, say, just the length of our parallel wires. Okay, and so let's say that both of our wires have some length L. Okay, and then we have B1, and then we would have the sine of the angle between B1 and L2. This L2 vector was pointing to the right, and the magnetic field B1 was into the screen. And so in this case, the angle between those is 90 degrees, and so this becomes a 1. And so we get I2L and B1. Where's B1? Mu naught I1 over 2 pi d. So it's mu naught I1 over 2 pi d. And so therefore, the force of current 1 on current 2 is equal to, let's reorganize a little bit, mu naught I1, I2 times the length of the wires divided by 2 pi d. They are anti-parallel. If the currents are parallel, this is an attractive force. If the currents are anti-parallel, it's a repulsive force. And by Newton's second law, it's probably the third law. This is the action-reaction. The force of 2 on 1 would have the exact same magnitude, but the direction would be opposite. So, for example, if there are parallel currents as we've drawn, then the force on 2 due to 1, F1 on 2, is an upwards force, attractive, and then the force of 2 on 1 is also attractive, but in order to attract current I1 to current I2, the force has to reverse its direction, as required by Newton's third law of equal and opposite action-reaction forces. Okay, good. So that's the force between parallel wires. What I want to do next is I want to start to think about a different kind of problem. And so this is the first topic in the last chapter that we'll cover. And so this is chapter 30 out of Knight. So chapter 30 from the Knight textbook. And so the topic that I want to discuss is motional EMF. Actually, I should mention before we do that, I'm going to, in the description of this video, I'm going to put a link to a demonstration that had been set up that shows the force between parallel and anti-parallel currents. And so it's a very convincing demo, and the video is less than a minute long, and so it's worth checking out. Okay, so look for the link in the description. So, motional EMF. So here's the scenario. We're going to set up a magnetic field, and we're going to make that magnetic field, it doesn't matter what direction it is, but let's put it into the page or into the screen. And I'm going to have a conductor that's immersed in this magnetic field. And so there's the conductor, and I'll draw some more magnetic field lines, like so. And what we're going to do is we're going to take that conductor and we're going to pull it through this magnetic field with some velocity v. Okay, and let's suppose that our conductor has some length L. Okay, so we want to analyze this scenario. In words, what we're going to do is we're going to pull a conductor, through a uniform magnetic field. We're going to analyze this a lot like we analyzed the Hall effect in the previous video. What we'll do is we'll say, well, let's imagine that we have some positive charge Q that looks a bit like a magnetic field line. Let me draw my positive charge as a red positive charge. Okay, and so let's see if we did, the velocity of this charge is to the right because the whole conductor is being pulled to the right, and the magnetic field is into the screen. So the force on our positive charge is FB is equal to QV cross B. And so if this is our charge Q, its velocity is to the right, so we put our right arm to the right. We curl our fingers into the screen in the direction of the magnetic field, and our thumb points up. So there's a magnetic force on our charge. Okay. The magnitude of this, so this is a vector equation, the magnitude of this force, because the magnetic field and the velocity are perpendicular, we get the sine of 90, which is just a 1, and so the magnitude of this force is QVB. Okay, but just like in the Hall effect analysis, if we take our positive charges and pile them up at the top of the conductor, that leaves behind negative charges at the bottom. Or if you want to think of a regular conductor like copper or something, it's really the electrons, the conduction electrons, that are forced to the bottom of the conductor, and that leaves behind an excess positive charge at the top. Okay, so the magnetic force causes positive charge to collect at the top of the conductor and negative charge to collect at the bottom. All right, so if we draw this picture again, here's our conductor. It's moving with velocity v. There are magnetic field lines going into the page. And what we end up with is positive charge collecting at the top, negative charge collecting at the bottom. If I had a positive over here, the magnetic force we've already determined is towards the top of the page. But now we're going to get an electric field inside our conductor. I'll draw it outside to save some space, but there's an electric field inside our conductor that points from the positive to the negative charge, and so that establishes an electric force on this charge Q that's inside our conductor. And once again, we're going to look for an equilibrium condition in which this magnetic and electric force balance each other out. Okay, so the separation of charge establishes an electric field in the conductor which exerts a force on Q that opposes the magnetic force. Okay. In equilibrium, we require that the magnitude of the magnetic force and the magnitude of the electric force balance each other out. When that happens, then we'll end up with a potential difference across our conductor that doesn't change, provided we keep pulling our conductor with this constant velocity v. So the equilibrium condition is, for the magnetic force, we have QVB, and for the electric force, we have Q times E, and so we can cancel the factors of Q, and so the electric field in equilibrium is equal to the speed with which we pull our conductor times the strength of the magnetic field that is applied. Okay, so the potential difference potential difference or EMF induced across the conductor is. Okay, so the induced EMF is, let's suppose we start at the bottom of our conductor, and so actually I'll go over here, and I'm going to say this is y equals 0, and then this is y equals L. So we're going to start at the bottom of our conductor, and then we're going to move in a direction dl that goes from the bottom to the top. So I'm going to calculate the voltage difference, which is the final voltage, which is the voltage at the top, minus the initial voltage, which is the voltage at the bottom. And that's equal to minus the integral of y equals 0 to L of E dot dl. But we saw that what's going to happen here is we're going to get positive charge at the top and negative charge at the bottom, and an electric field that points from top to bottom. And so the essential point here is that the electric field E and the dl vector are antiparallel. So if we go back to here, then we could say E and dl are antiparallel. Therefore, E dot dl is equal to E dl cos of 180 degrees, which is a -1 for that cosine. And so this induced EMF is going to be equal to minus the integral y equals 0 to L of minus E dl. The electric field in our conductor is constant. It's like a charged capacitor. And so we pull out the minus E. The two negative signs cancel, and we get E dl from 0 to L, which is just equal to E times L. Okay, but E is equal to V times B, such that the EMF is equal to V times B times L. And so this is the motional EMF induced across our conductor that is moving through a uniform magnetic field. All right, good. So that's kind of interesting. Now, calling this an EMF is suggestive. It's like, well, what else do we know that creates an EMF? It's a battery. And how do we use batteries? We use batteries in circuits to create currents. And so could we use this motional EMF to establish a current in a circuit? So let's see. Induced current via motional EMF. So here's the setup. We're going to have, again, we're going to have a uniform magnetic field, and I'll try to draw quite a few of these this time. So these are our magnetic field lines going into the screen, and it is uniform. So it's constant everywhere. And what we're going to do is we're still going to do the same thing. We're going to take a conductor and we're going to drag it through this magnetic field. And so we have a conducting bar, let's say. So this is a conducting bar. And what we're going to do is we're going to give that bar a velocity v. And now we know that if this magnetic field is constant b, then we'll get an induced EMF across our bar, and that induced EMF will be equal to the speed times the magnetic field times the length of this bar. And so we already saw that we would get positive charge collecting at the top and negative charge collecting at the bottom. Okay, and let's see, what could we do next? What I'm going to do is I'm going to draw it in a different color. I'm going to take some conducting wire. And what we're going to have is our bar sliding along this conducting wire. And what it does is it completes a circuit. And so maybe somewhere in that circuit we place a resistor R. Okay. The last thing that we'll do is we'll say that our bar has a length equal to L. Okay, well, we saw that if I had a positive charge inside of this bar, that there's a magnetic force on it upwards, and so the direction of motion of positive charge is also the direction of current. But now what will happen is, instead of just having a whole bunch of charge being collected at the top and bottom of this bar, because we have a complete circuit so that these blue tracks, this is a track made from conducting wire. Because our track is conducting, we can have the current flow through the conducting wire, and it completes a full circuit because it just comes back into the conducting bar and completes the loop. And as the bar is pulled further to the right, just the area of our track gets bigger, the area of our conducting loop gets bigger, but the current can be sustained. Okay, so let's see. A lot of the analysis we already know. The motional EMF is VL times B, and our equivalent circuit looks like a single resistor and a single source of EMF, which we could model as a battery with a negative and a positive terminal, and that's going to establish a current I. And we know that IR is equal to the EMF, or I is equal to the EMF over R, and EMF is VLB over R. And so what we get is a constant current, provided we maintain a constant velocity of the bar. So if we maintain a constant velocity, or let's just say constant speed v of our bar, we get a constant current I. Okay, now let's think about this a little bit, because we know that, let's do it in black. We know that the force on a current, the magnetic force on a current was something we just worked out, was I L cross B. Okay, so remember what the L vector, how it was defined. It was defined to be a vector that had a magnitude of length L, and its direction was in the direction of the current. So in this case, it's towards the top of the page. So if we evaluate L cross B, our right arm goes towards the top of the page, our fingers curl into the screen in the magnetic field direction, and there's a magnetic force, FB, that points in the direction of our thumb, which is to the left of the screen. And so there is a magnetic force, FB, on our current carrying bar. So, but this current is in a magnetic field, so there is a magnetic force on the current. And so if I want to move my bar at a constant velocity to the right, I must exert a force that exactly balances this magnetic force so that the acceleration of the bar is 0 and it has a constant velocity. So we must supply a constant force, maybe it's called F pull or something like that, to keep, let's be a little more detailed, to balance F magnetic such that the bar moves at constant velocity. At constant velocity. Okay. So let's actually calculate the magnitude of this magnetic force. It's going to be I times L times B is the magnitude. So the magnitude is ILB, but I was VLB over R, so that's equal to VLB over R times L times B, which is V L squared B squared over R. And so our F pull, we require F pull to have that same magnitude but being in the opposite direction. Okay, so over here we would have to supply a force F pull, and we've now calculated what the magnitude of that force would have to be. Let's do one more thing. One more analysis in this problem, and the type of analysis I want to do is an energy analysis. So I want to calculate the work by F pull. So what is the work required by F pull to maintain a constant velocity of the bar? Okay, so the way we calculate work is force times displacement, right? In general, it's the integral of f dot ds, where ds is an infinitesimal displacement. Now, what we're trying to do is we're trying to pull our bar towards the right. So this is our ds. And we have a simple case where F pull and ds are parallel. So this is equal to just the magnitude of F pull times the magnitude of ds, since F pull is parallel to ds. Okay, but F pull was just a constant. We calculated it's v L squared b squared divided by r. Those are all constants if we're trying to maintain a constant speed. And so this is equal to just F pull, the integral of ds, since F pull is a constant. Okay, and so that means that the work is just F pull times whatever the total displacement delta S ends up being. So remember, work is an energy. And what we could do is we could calculate a power by the change in energy in a given amount of time, delta T. So the input power is, let's say Pn is equal to the work that we get per unit time delta T. And so that's going to be F pull times the displacement of the bar divided by the time interval. But how far the bar moves in a given amount of time, so delta S divided by delta T, is just the speed of the bar. And so that's just F pull times V. And so therefore Pn is equal to, well, F pull is right over here. It's V L squared B squared over R. And we're just going to multiply by another factor of V. And what we end up with is V squared L squared B squared over R. So this is the required input power in order to sustain this constant current by moving the bar at a constant speed. So let's compare Pn to the power dissipated by our resistor R. Right, what the resistor might actually represent is some kind of device that we're trying to operate with this current. And so we're using the energy of the current to run some kind of device. And so we want to know how much power does this device dissipate. So the power dissipated by a resistor, one of the ways we could calculate that was I squared times R. But the current I, if we go back, that's something we calculated. It's VLB divided by R. Sorry, VLB divided by R. Okay, so current is VLB divided by R. and then we're going to square it, and then we're going to multiply by r. And so what we get is v squared, L squared, B squared, and then r divided by r squared is just a 1 over r, and these expressions are exactly the same. And that's a good thing because it tells us that however much power we put into our system, we get an output power dissipated by our resistor, the power dissipated by our resistor that is exactly equal to that. And so therefore, P in is equal to this power, the useful power dissipated by our resistor, and we have energy conservation. Okay, so this example is a good one because it's the first example in which we were able to see an induced current created by a magnetic field. So we just had a conductor which had free charge within it, so these conduction electrons that are able to move. And if we just pull the bar through a static magnetic field, we get this induced motion of charge, which created the current, and we described that as an induced EMF. If you think about it a little bit, how do you actually get charge to move? Well, you use electric fields to move charges. And so where we're going to head towards, as we get towards the end of the term, is that we're going to try to see that we can use a magnetic field to induce electric fields that will then interact with static charges. So that's something that we can look ahead to. All right. Thank you very much.